Hi, everybody. It's Professor Mitchell. We are now wrapping up our coverage of Chapter 2. You may remember I mentioned, I think, when we started Chapter 2 that I was not planning to do Section 2-4. We are going to do everything we need to do with scatter plots, correlation, and regression toward the end of the semester. So the last section that we're going to cover, 2-3, is called Graphs that Enlighten. So these are good graphs. Other types of graphs that we haven't talked about yet, and also graphs that deceive. So you want to be on the lookout for these. And I actually have seen some bad graphs in various places. Okay, so just be on the lookout. You know, turn on your critical thinking when you look at a graph. Okay, so I think this is basically what I just said. So introducing other common graphs that you see often that are good for different things. Discussing some deceptive graphs that give you wrong impressions or somehow misleading. And you can use technology to create graphs. I am not going to go into that in any sort of detail because people have different access to different kinds of technology, but that's something that I'd be happy to work with you, one-on-one if you're curious how to do that. All right, so first, some good graphs. A dot plot is a graph of quantitative data in which each data value is plotted as a point or dot above a horizontal scale of values. So here is an example of a dot plot. It kind of accomplishes the same thing as a histogram. It's a little easier to make because when you have a list of data in front of you, you can, instead of making tally marks like we did when we were creating the frequency tables, you can just literally create this axis and then start putting dots above the different numbers. So they are really, really easy to make, and they give you a good picture of the shape of your distribution. Okay. All right, the next example is, oh no, sorry, still on dot plots. I think that this is basically what I just said. Oh, notice that it is usually possible to recreate the original list. That's something you can't do with a histogram. So let's go back to this, their example here for a second. So it looks to me like, well, I'm looking at this range between 50 and 60. Sometimes in a dot plot, literally each stack of dots represents a different number. It looks to me like they might have these grouped in classes of 2, of width 2. This might be 50, 51. This might be 52, 53, 54, 55, 56, and 58. It looks to me like they're grouped in classes of 2. But oftentimes with dot plots, they are in classes of 1, which just means each different number gets its own stack, okay? And so you might not be able to exactly recreate the list from this one, but you could come pretty close. Okay. All right, the next kind of good graph, and this is a favorite of mine, is called a stem plot or a stem and leaf plot. Back in the old days when I first started teaching, before I learned how to use Excel, I used to actually use this to figure out what does my distribution of exam scores look like. So the way it works is, and again, represents quantitative data, so numerical data, by separating each value into 2 parts, the stem, such as the leftmost digit, and the leaf, such as the rightmost digit. Okay. So here is an example. Yes, here's an example of a stem plot. Oh, goody, this is the original list of the pulse rates. And they're all even numbers for some reason. That's interesting. Okay, so that first row means that the slowest 2 pulse rates were 40 and 42. And then 50, 50, 52s, a whole bunch of them, a bunch of 54s, a couple 56s. You see how I'm reading that? So the tens digit of the pulse rate is over here. That's called the stem. And then the ones digits are called the leaves. It is a quick and easy way to put a set of data in order. So I don't know exactly how many there are here. Looks like there might be about 100. So if somebody gave you this list, you know, that they just collected, it would not likely be in numerical order. So if you were trying to put it in numerical order and you didn't have access to any technology, you could just make a stem and leaf plot. Okay. Features of a stem plot, it again shows the shape of the distribution. It does retain the original data values. Now, I want to clarify this last one. It says the sample data are sorted. Well, when you make what I call your first draft of a stem plot, it's probably not perfectly sorted, all right? You'll have your 40s together, your 50s together, your 60s together, but within the 40s, 50s, and 60s, they won't be in order. You have to make a second draft where you then put your leaves in order within the 40s, within the 50s, within the 60s. So it does not come out perfectly in order when you first do it, but it makes it easier to put the stuff in order. Okay, so I decided on the fly here that it would be good to see an example of kind of how a stem plot is formed. So I made up this example, very small set of data. I hope you can see it on the video. It goes 24, 21, 18, 13, 32. And then on the second row, it goes 36, 18, 23, 35, 35. And then on the last row, it goes 16, 13, 26, 28, 18. So to make what I call the first draft of your stem plot, notice that the data goes from the teens to the 30s, okay? So my stem is going to have 1, 2, and 3. And then I went through the list just in the order that it came, and I started putting in the leaves. So the 24 went here, the 21 went here, the 18 went there, the 13 went there, and the 32 went here. And then you just continue like that all the way through until you come up with this. And then you do want to put each of those rows in order. And if your data set is not, you know, huge, it should be pretty easy to put those in order. So for example, 838, 638 became 336, 888. Okay. This is a very, very small data set, so we don't really use a lot of those descriptive terms like normal or skewed or anything. Those are really for larger sets of data. I'm just noticing this one is reasonably uniform. All right, there's 6 here, 5 there, 4 there. All right, so they're pretty close to being, you know, just about the same frequency for each group. Okay, next we have time series graphs. A graph of time series data, which are quantitative data that have been collected at different points in time. I think we talked about time series data maybe back in chapter 1, such as monthly or yearly. All right, and you've probably seen a graph that looks like this at some point. Law enforcement fatalities by year. Okay. So you just get the number for each year. The Dow Jones average is often plotted like this. Another one is presidential approval rating, you know, changes over time. And then if you see any really high, you know, peaks or valleys, you can talk about why did that happen in that year. So for example, I'm going to throw a theory out there. I have a feeling that this peak in law enforcement fatalities in 2001, that could have had something to do with 9/11. Okay. That's really the most dramatic one that I see up here. I don't really have a theory about any of the other ones. All right. They're not all that dramatic, the other, you know, drops and spikes. It's just, you know, it's kind of Kind of random. Okay, but that's one possible theory for 2001. Okay, so features of a time series graph. It reveals information about trends over time. And that's about it. Okay, does that make sense? All right, then we will move on. When we talked about histograms, I mentioned bar graphs. A histogram is not technically a bar graph. Bar graphs are used for categorical data, qualitative data, data that are words, for example. If I took a survey of everybody's favorite ice cream flavor, okay, I can make a bar graph out of that. Okay, hopefully there wouldn't be 35 different answers. Okay, there probably wouldn't be. And when you have, usually when you make a bar graph, if there are more than about 6 or 7 different answers, you take the ones that were mentioned the least frequently and you just group those under other. Okay. So if your favorite ice cream flavor happens to be rum raisin, all right, I don't think you're going to have a ton of company on that. All right, maybe you would, but you might end up under other. Okay. Feature of a bar graph, don't they have an example here? I think they do somewhere. Shows the relative distribution of categorical data so that it's easy to compare different categories. Okay. All right, and then a Pareto chart is a specific kind of bar graph. It's a bar graph where the bars have been arranged in descending order. So if the #1 favorite flavor of ice cream is chocolate, that would be first. And if the #2 favorite flavor is vanilla, that would be second. Okay. All right, so again, the same feature as a bar chart, shows relative distribution. It's easy to compare different categories. And additionally, if you put the categories in descending order, it draws attention to the more important categories. And I'm looking for an example here. If I don't see one, I'm going to make one up. Ah, there we go. Perfect. Okay, so this is a Pareto chart of stolen boats by type. So they're reading this. What I'm getting from this is that there were exactly 5 types of stolen boats: jet skis, motorboats, utility boats, inboard, and sailboats. Okay. And then it shows you how many were stolen. So it looks like almost 1,400 jet skis. You know, they're kind of small, maybe easier to steal than other kinds of boats. Motorboat, almost 1,000. Utility boats, about 400. Inboard, maybe about 350. And then sailboats are very large, right? They're probably pretty hard to steal. Less than 50 of those. Okay. That's an example of a Pareto chart. And again, what makes it a Pareto chart is that it's the categories are in descending order by frequency. If they were just kind of all over the place, you know, maybe alphabetical or something like that, that would just be called a bar chart. All right, another kind of good graph that everybody's familiar with is a pie chart. Again, is used for categorical data as slices of a circle, where the size of each slice is proportional to the frequency count for that category. Okay. Shows the distribution of categorical data in a commonly used format. Everybody understands how to read them. Okay, so here is the same data that you were just looking at as a pie chart. Okay, so one thing that I get out of this that I did not get out of the Pareto chart is that nearly half of stolen boats were jet skis. That did not pop out at me when I was looking at the Pareto chart. Okay, a little over a quarter of stolen boats are motorboats. Okay, and then the other types altogether make up less than a quarter. Okay. When you're making a pie chart, if you have to make one by hand, remember that there are 360 degrees in a circle. So if you notice, for example, that, you know, your biggest category takes up 45%, you should make, here, I'll do this here real quick. You should make that biggest slice of the pie be, let me see if I can do this really fast. I think that's 1800. This is 1440. It should be 162 degrees, I think. Okay, that biggest piece of the pie should be 162 degrees. Okay, roughly. It doesn't have to be perfect. And again, you can make these things with Excel. It's actually very easy to make a pie chart with Excel. I've done it. Okay. Then we have frequency polygons. That's using line segments connected to points located directly above class midpoint values. Very similar to a histogram. Okay. I don't really see any reason, you know, why you would pick a frequency polygon over a histogram versus, you know, the other way around. They do almost exactly the same thing. Here is your McDonald's. I think I like the histogram a little better, personally. Here is the McDonald's service lunchtime in seconds. So where they got this 99.5, that is the class midpoint for 75 to 124. Okay. 149.5 is halfway between 125 and 174. Again, I'm referring back to that frequency table from the first section. Okay. Properties of a frequency polygon. Oh, well, I guess they're pretty clear. They're just pointing out to you that you can also have a relative frequency polygon where you use proportions or percentages instead of raw frequencies. Okay. So, for example, if you wanted to compare drive-through service times for Dunkin' Donuts and McDonald's, you could do it like this. And you would almost definitely want to use relative frequencies for that, especially if your data sets have different sizes.